Hello students, welcome back. Let's go to section 2, Lagrange theorem. Here's the statement. Let H be a subgroup of a finite group G, then the order of H divides the order of G. Here's a symbolic statement. The order of H divides order of G, so the order of G divided by order of H should be an integer, and it has to be a positive integer because everything here is positive. We are dealing with the order subgroups. This quantity here, the order of G divided by order of H, is called the index of H in G, and we denote it as, well, this notation with colon, G colon H, the index of H in G, and that quantity is nothing more than this fraction expression. Okay, how do you prove this? We do it in two steps. First, let H be a subgroup in G, then all cosets of H share the same cardinality. So there are many cosets. H itself is a coset because E times H is H, and then A times H, B times H, and so on and so forth. But we are dealing with finite group G, so there should be finitely many, and they all share the same cardinality. So the cardinality of H times the number of cosets, and that's going to be the cardinality of G. The number of cosets here is called the index in this case, but in any case, we have to prove this lemma. How do you prove it? Well, all we have to do is to establish bijections. We define like this. A map H to AH, like this, FA of H is A times H. And then for right coset, do the same thing. H to HA by GA of H is H times A. So I claim this is a bijection from H to left coset AH, and this is a bijection from H to right coset HA. I'll do the usual. I'll prove only for the left coset, and the technique for the right coset is pretty much the same, and I'm going to leave that to you. So we have to prove that this is a bijection, 1-to-1 and onto. Let's see. It should be 1-to-1. That means if I have same function value, so AH, with the same, then I should have begun from the same H value there. And then onto, this will have to cover everything in AH. That's a little bit easier to see, I guess. AH is given by all the A times a member of H form. In any case, here's the proof. The onto part is a little bit easier, so let's do that first. So AH consists of elements of this form, A times a member of capital H. And that's A times H is actually FA of H, a function value based upon a function defined like this. Consequently, that arbitrary element from the left coset AH belongs to the image set. So we have onto map. Now how about 1-to-1 map? Let's suppose the function value is the same. FA of H1 is equal to FA of H2. In other words, by definition, AH1 and AH2 are the same. You see, same function value. Does it mean the same H value? And that's easy because all you have to do is remove those A's. How do I do that? Multiply by the inverse. Multiply by the inverse. Yes, we are talking about a group, so inverse always exists. Cancel out and we get H1 is equal to H2. That proves that this map FH is an injection as well. So 1-to-1 and onto, so we have a bijection, so we have to have the same cardinality. As for the right coset, I'll leave that to you. Exactly the same technique, but you have to apply that to your right. By the way, I do have proof here, by the way. Okay, so what did he establish? All cosets share the same cardinality. And then, what is the number of cosets? Multiply those, then you're going to get the cardinality of G. Indeed, all cosets share the same cardinality, so we can take those disjoint union. Remember, we have to have disjoint union because all those cosets are equivalent classes. Remember, equivalence classes are either disjoint or identical. Nothing in between. So identical, in that case, duplicates. So you can throw those away, and they're different, and then they are disjoint. So union them all, then you're going to get disjoint union. And we are talking about finite number of elements anyway. So there are m such cosets, m left coset. Do the same thing for the right coset, and we have n right cosets. And then if you count, m and n, of course, will have to be the same. And they have to be the cardinality of G divided by cardinality of H, which we call the index. So that proves Lagrange's theorem and established the concept of the index. Okay, now that we proved Lagrange's theorem, let's go ahead with some corollaries. The order of an element of a finite group divides the order of the group. So what is an element of, order of an element? That means the order of the cyclic group generated by that element, right? But then again, we proved that cyclic subgroup is a subgroup of the original group. So that order must divide the order of the original group. That's all there is. So instead of considering the order of an element, let's consider it as the order of the cyclic subgroup, and that's it. Next, a finite group of prime order is cyclic. Let's see. Prime order, let's see, order is P for prime, then it has no non-trivial divisor. 1 divides P, and there's nothing else other than P itself. So if you have a cyclic subgroup there, yes, take any element, and then you can form a cyclic subgroup there. And then if that element happens to be the identity, then you have order 1, and 1 divides P, of course. No problem there. Now, if that element is not identity, then at least 2 elements are there, identity and that particular element. And that order must divide P, but P is prime, so that cyclic group will cover everything. Consequently, we end up with a cyclic group generated by that element. So whatever non-trivial element will generate entire G. Yeah, I went into extreme detail here, but I don't think that's really necessary here. And if you really want to be really precise, go ahead, follow everything. Now, K is a subgroup of H, and H in turn is a subgroup of G, and that the index of K and H and the index of H in G are both finite. This and that, well, this is nothing more than this. G, index of K in G, that means cardinality of G over cardinality of K, and that's the, let's see, let me copy and paste this thing, and then that once more, and then this is HK GH. That's it, isn't it? We are talking about finite indices anyway. They're all finite, so we can do this kind of computation. And then this one is the first index, And this one is the second index. And then the third index is just a product of those. Because both blue and green are finite, this has to be finite as well. Okay, so much for 2.2. And let's go to an example problem. Give an example of the desired group and its subgroup if possible. If impossible, explain why. A subgroup of an abelian group whose left coset and the right coset give different partitions. What do you think? Example or impossible? It's gonna be impossible because we're talking about abelian groups, so left coset and right coset are the same. Remember, the group operation is commutative, so multiplication to the left versus multiplication to the right are identical. So there should be no difference. So that's impossible. B, a subgroup of a group of order 6 whose left coset gives a partition of the group into 6 cells. Alright, Lagrange theorem says the order of the group is divisible by the order of the subgroup, right? But here, in this case, you have 6 divided 6. And that's 1. So we have to start from a subgroup of order 1. Is there such a subgroup? Well, yes, of course. The trivial subgroup, just identity E, and that's it. So based upon that, try to come up with an example. Try to find an abelian example, which is going to be easier, and then a non-abelian example. In this case, it's equally as easy because we are considering a trivial group only. How about C? A subgroup of order 6 whose left cosets give a partition of the group into 4 cells. Okay, Lagrange theorem says 6 divided 4 is 3 over 2, which is not an integer. This is not an integer, so it's not going to work. Remember, Lagrange theorem says the order of the subgroup must divide the order of the original group. So order of subgroup times 4 must be 6. That's not possible. Now, if I change it into something like this, then that's going to be okay. In this case, the order of the subgroup has to be 2 because you see, 6 divided by 3 is 2. So the order of the subgroup is 2, and then 3 cells, 2 times 3 is 6. So yes, you can think of some group of order 6 and a subgroup of order 2, and then you can find the partition of cosets. And the problem asks you about the left coset, but you can do right coset as well. And also think about both abelian and non-abelian example. Abelian example is going to be, of course, easier. Similar problem here, group of order 12 and partition into 4 cells. Is this possible? 12 divided 4 is 3, so yes, it's going to be possible. If you begin with a subgroup of order 3, then 3 times 4 is 12. Yes, it'll work. So think about an abelian group of order 12 and a subgroup of order 3. And then after that, a little bit bigger challenge, think about a non-abelian example.